Okay, so help me out throughout the lecture. So we will discuss these questions. So, humidity is a topic where you need to what? Live with the theory. So when you do these questions, it's actually testing whether you have really understood the concepts. So don't worry, certain questions, sometimes you have to be with those questions for several weeks or maybe days. It depends, right? But live with those questions. Don't give up. Okay? Live with the questions, live with the theory. You're going to be fine, right? So we're going to start then. So we'll start off. So we have 5 MCQs from humidity. We'll go one by one, right? Okay. So the first question is a very simple question. The concentration of water vapor inside a closed room at a certain temperature is 24 gram per centimeter cube, and the relative humidity is 60%. If the air inside the room is made to saturate with water vapor at the same temperature, the new water vapor concentration inside the room is. So you need to understand if it is the same temperature, will the saturated vapor pressure change? No, right? Saturated vapor pressure does not change, right? So, and you have to understand this is a closed room, so the volume is also the same, which means the mass of water vapor needed to saturate is going to be the same, right? So now you need to understand this concept again. So now what have they given us data? So in the closed room, we have what? Relative humidity is 24 gram per centimeter cube. So, sorry, the absolute humidity is what? 24 grams per centimeter cube. Because the concentration of water vapor inside the closed room at a certain temperature is 24, which means they're talking about the absolute humidity, right? Remember, what was the definition of absolute humidity? The water vapor density in a certain space, right? So then we have 24 gram per centimeter cube. Okay, so now let's see. Relative humidity is 60%. Now you know mass available divided by what? Mass to saturate that space multiplied by 100% is equal to what? The relative humidity. Now you see the relative humidity is 60%. That's equal to what? The mass available M divided by what? Mass to saturate multiplied by 100%. Now tell me, what is the other equation that we learned? So we know if you divide by V, we can get what? Density of water vapor available divided by what? Density at saturated state, rho S, multiplied by 100%. So rho means what? The density of water vapor in the available space, which is the absolute humidity. So 60% is then equal to what? So what is rho? 24 gram per centimeter cube divided by rho S multiplied by what? 100%. Okay? So we're going to saturate it
Yes.
now. When you saturate it, what's going to happen? When you're going to saturate it, what is going to happen? Relative humidity becomes 100%, right? Now, so I can isolate rho S. What is rho S equal to then? Basically 100 over 16 to 24, right? 100 over 16 to 24. So we can simplify easily. What's the answer that you get then? 40 gram per centimeter cube, right? Very easy question. But I explained the theory also, just to remind. Okay? Okay, and then this one. So atmospheric air, actually, this should be atmospheric air at 30 degrees Celsius having 80% relative humidity is made to flow slowly through two large chambers, Y and Z, maintained at 0 degrees Celsius and 40 degrees Celsius, as shown in the figure. Densities of saturated water vapor in the atmosphere at 0 degrees Celsius and 30 degrees Celsius and 40 degrees Celsius are 4.8, 30, and 48 multiplied by 10 to the minus 3. So always it's what? 10 to the power minus 3, right? So now, which of the following tables correctly represents the relative humidities and the absolute humidities of the air in the atmosphere, X, and the chambers, Y and Z. So what you need to understand here is that, if you observe this carefully, atmosphere, if you think about the atmosphere, the relative humidity is what? 80%. But you know the saturated vapor density, right, in the atmosphere is equal to what? What's the saturated water vapor density in the atmosphere? Atmosphere is at 30 degrees Celsius. So you know at 30 degrees Celsius, the saturated water vapor density is what? Given to be 30 times 10 minus 3, right? Okay. Now, if you think about relative humidity is 80%, then you can find out what? The absolute humidity, right? So, you know, density available divided by density to saturate multiplied by 100% is equal to what? Relative humidity. This is the absolute humidity. Density of water vapor available is the absolute humidity. Now, if you think about atmosphere, which is X, tell me what's the relative humidity? 80, right? And so we need to find rho. So what is rho S then? Rho S is equal to what? 30 times 10 minus 3, right? And then this is what? Multiplied by
into 100.
100%. So then, I mean, you don't have to do it like this now. Of course, it's going to be 24. You can do it mentally, right? So it's going to be 80. See, now 80% now. So if you're going to get the available thing, you have to multiply it by what? 80%. If you multiply the absolute humidity at saturated state, right? This is the absolute humidity at saturated state now, or the saturated vapor pressure density, right? Saturated vapor density. So if you multiply 30 times 10 minus 3 by 80%, you're definitely going to get what? The absolute humidity. No? So do it mentally. 80% of 30 times 10 minus 3 is going to be 24 times 10 minus 3, right? So you don't need to write equations for these things. Okay? Are you all following this? Right?
Yes, sir.
Okay. Okay. And now, also, okay, if you think about room Y now, what happens? Now tell me, when the water vapor comes from the atmosphere into the room Y, what's going to happen? See, the absolute humidity at saturated state, or we can say the saturated vapor density in room Y is going to be how much? That's going to be 4.8 times F minus 3, right? Yeah. So that means
The
we need to
maximum
have,
water vapor the air can hold at 0 degrees Celsius.
yeah, per centimeter cube per unit volume, right? So we're talking about density now. So 4.8 times 10 minus 3 is the amount we need per centimeter cube to saturate what? Room Y. Is that okay? Right. But when air is coming from the atmosphere into Y, what kind of air is coming? Air that has a density of this much is coming, right? Because 80%, right, is the absolute humidity of the air in the atmosphere that's going to get into room Y, right? So what is the vapor density that's entering room Y? Yeah, that's going to be 24 times 10 minus 3, right? Is that clear? Okay. Then actually, this is more than the requirement to saturate room Y, right? Because room Y is at 0 degrees Celsius. To saturate room Y at 0 degrees Celsius, I only need 4.8 times 10 minus 3. But I'm bringing how much? 24 times 10 minus 3, which means I have
The air,
excess. It's going to condense. Is that clear? Air is going to,
yeah,
sorry, not the
condense.
air, the water vapor is going to
Excess
condense.
water. Air
So
is becoming saturated. No, sir.
the space is going to be saturated. Space is going to be saturated. Room Y is going to be saturated, which means the excess is going to be condensed. So what's going to happen then? Now, okay, now let's look at room Y then. Room Y is going to be 100% what? Saturated. If room Y is going to be 100% saturated, do I need to have to do a calculation? No. Why? Because I know when room Y is 100% saturated, the saturated vapor density is there, right? So what is the saturated vapor density? Yeah, 4.8 times 10 minus 3. So then that tallies, no? Right? It tallies. So 100% relative humidity means you have entered the saturated state. Now from room Y, you're going to enter what? Room? Yes, you're going to enter room Z, right? Now tell me, if you look at room Z, now what kind of water vapor is going to enter room Z? What kind of water vapor is going to enter room Z? Water vapor that has a density of 4.8 times 10 to the power minus 3 is going to enter room Z, right? Because that is the density that we have now because the X is condensed, right? So now in room Z, what are we having? What are we having? We are going to have what? 4.8 times 10 minus 3. So that is the absolute humidity that we have, right? 4.8 times 10 minus 3. But now tell me, what is the saturated vapor density or the amount of water vapor per unit volume that I need to saturate room Z? That is going to be what? 48 times 10 to the power minus 3, right? Okay, so these are rho and these are rho s, right? Then if you divide rho by rho s and multiply by 100%, you get what? The relative humidity, which turns out to be 10%, right? So there we go. The answer then is the second one. Is everybody clear with this?
Yeah, sir, it's clear.
Very good. Okay. Now, the third one. When a person wearing spectacles moves from room P to room Q, he observed that a thin film of water is deposited on the lenses. Nice question. Consider the following that are given as necessary conditions for this to happen. So what can we say? Yeah. When you are going from room P to room Q, the spectacles, what can you see in the spectacles? You can see water vapor deposited. How is this possible in the first place? Of course, you need to go from a colder room to a warmer room, right? Otherwise, how can the water vapor condense? Clear? So now tell me, what's actually happening when you go from room P to room Q? You're taking your cold glasses and you're going to room Q. What happens is, when the temperature is higher, what is happening? The dew point is going to be higher. You know that, right? When the temperature is higher, dew point is higher. So when you go from room P to Q, the dew point is higher. But you see, the spectacles have a low temperature because you're going from a cold room to a warmer room. So the cold spectacles have a lower temperature. They might have a lower temperature. The spectacles might have what? A lower temperature than the dew point of what? The warmer room, the hotter room, or the room with the higher temperature. Because the dew point in the room with the higher temperature is greater. So then what happens? The temperature of the spectacles is going to be less than the dew point of the hot temperature room. Then what's going to happen? Then water vapor is surely going to condense. Because when the temperature for the water goes below what? Goes below what? The dew point is definitely going to condense. The other thing that you can think about is that when you go from a cold room to a warmer room, you know that the water vapor molecules in the warmer room are going to have a greater temperature than what? The spectacles, right? So then heat can be released from the hot vapor molecules when they deposit upon the cold surface, releasing heat and therefore condensing, right? Is that clear? Now, you
Yeah,
need to
sir.
understand this further. Now, if the relative humidity, now, does that really have an effect? Now, see, this is kind of a tricky question. Okay, I'm going from the colder room to the warmer room. So my question is that, okay, is the relative humidity really important there? What matters is the act of condensing, right? So they are asked in the question, which of the following conditions should be satisfied for the above phenomenon to take place definitely? So the question is definitely, right? Should happen definitely. So if it's going to happen definitely, for sure, now see, okay, when you go from the cold room to the warmer room, you need the water vapor to condense upon the cold spectacles. You just need that process to take place, right? For sure, you need that process to take place. But if you have more water vapor, then more condensation will take place. But having more water vapor is not absolutely necessary for the process to work. Exactly, what's necessary for the process to work is that the room Q should have a greater temperature than room P. That's all that's required, right? I mean, if you have more water vapor, then you can condense more of it. But that is not absolutely necessary for the process to work. Of course, you need to have some kind of water vapor, right? So it doesn't have to be greater, right? Exactly. You just need some water vapor to condense because the criteria for condensation is what I just mentioned. When you go from room P to Q, you need to take the temperature below the dew point. Is that clear? Right?
Yes,
Yeah.
sir.
Now, question number 4. This is a very good question. Absolute humidity is of air inside three closed rooms, A, B, and C of volumes VA, VB, VC at atmospheric pressures as A, as B, as Z. The dew point of air in room A is T naught. When the doors are opened as shown in the figure B, and the air in the three rooms are allowed to mix, the common dew point of the three rooms will remain at T naught if. So basically, when you go from setup A to setup B, if you need to have the same dew point, you need essentially to have the same environment. This is the IQ you need to think like this, right? This is the IQ part of it, to feel this picture. See, when you go from A to B, if you have the same environment, we have the same water vapor density per unit. See, water vapor density means the amount of water vapor per unit volume. If you can have the same amount of water vapor per unit volume, then for sure, what's going to happen? For sure, the dew point is going to be the same, right? Is there a reason for it to change if the environment is not different per unit volume, right? So then you need to understand when you go from A to B, for the dew point to be the same, I mean, if you want the dew point in room A to be what? The dew point when all the rooms are opened, if you want the dew point in room A to be the dew point when all the rooms are opened, you need to have the same environment that you had in room A now in the entire system. Is that clear? The entire open system, which is when you have A, B, and C together opens up, right? It becomes an entire system that's interconnected. So then you need to understand the environment that I had in A has to be the same per unit volume in what? B. Okay, which means what? The which means this the water vapor density in room A has to become equal to what? The water vapor density in the entire system that is shown in figure B. Is that clear? So
Yeah, so
what is
that's
the
clear.
mass of water vapor in room A? Is A VA. You know, the absolute humidity is the water vapor density. If you multiply by that by the volume, what do you get? The mass of water vapor. So SAVA, here we have SBVB, here we have what? SCVC. So now what's the total mass of the water vapor? That's going to be what? SAVA plus SBVB plus what? SCVC. That is going to be the total mass, isn't it? Total mass of water vapor. And now tell me if you need to have the same dew point in the entire system B to be the same as of A, you need to understand in this system B, I need to have the same water vapor density, which means what's the density in B? You can tell the total mass in B is what is B in the sense I'm talking about figure B, the entire system. So I'll call it the entire system. What's the entire mass in the entire system? SAVA plus what? SBVB plus what? SCVC. Okay, that's the total mass, right? You divide this by what? The total volume, which is VA plus VB plus VC. That should be equal to what? SA, which is the water vapor density in room A. So you can see here, you can multiply and you can get SAVA plus SAVB plus SAVC equals what? SAVA plus SBVB plus SCVC. So this cancels off. So you can see SA I can take out VB plus VC, VB plus VC is equal to what? SB VB plus SCVC. So the answer is SBVB plus SCVC divided by VB plus VC. Right? Answer is the first one. Okay. Right. The last question was the last question. Biscuits of a freshly opened packet of biscuits were placed in a container and it was tightly closed with a lid so that the air cannot enter or leave the container. The initial relative humidity inside the container was also found to be 80%. After a few days, it was found that the relative humidity inside the container had decreased to 30%, and the mass of the biscuits had increased by m. If the temperature inside the container remained constant throughout, the mass of water vapor initially present inside the container is. Okay, it's a very simple question. See, okay, initially we have 80%, right? Relative humidity. So it's keeping the biscuits. And then after some time, it's noted that the mass of the biscuits has increased by m, right? Increased by m. And the relative humidity of the space surrounding the biscuits has become 30%. It has decreased to 30%. That means what has happened actually is that the biscuits have absorbed the water vapor. And therefore, what has happened? The relative humidity has dropped. Okay? Right. Now, what you need to understand is, now, if the temperature is the same, see, temperature inside the container remain constant. So if the temperature is the same, definitely the saturated, the mass that we need to saturate that volume is going to be the same, right? Okay. So what we can write, you see, relative humidity equals what? Mass available divided by mass to saturate multiplied by 100%. I can say, I think I've told this in upthrust also. Upthrust is equal to what? Mg. Change in the weight is equal to what? Change in the upthrust, right? So now what you can see is, if I change the mass, see, if I change the mass, if I cause a change in the mass, and if I divide that by mass to saturate, multiplied by 100%, I get the change in the relative humidity, right? Exactly. If I change this only, the relative humidity changes. So what can I say? Okay, what I can say is that the change in the mass is m. Change in the mass is m. Why? The biscuits have absorbed water vapor by an amount m. That's the mass of water vapor that the biscuits have absorbed. So the change in the mass of the water vapor is m. That if you divide by ms, multiply by 100%, that's equal to what? The change in relative humidity, which is what? 30. The change in the mass can cause what? The change in the relative humidity. Is that okay with everybody? If I change the mass, I can change the relative humidity, because you can understand here, the mass to saturate does not change, right? What you need to understand now is that the change in the mass is equal to what? The mass of the water vapor absorbed by the viscous, which is m. You divide this by ms, multiplied by 100%. You get the change in relative humidity. Relative humidity has changed from 80% to what? 50%, 30%, right? 80% to 30%. That means the change in the relative humidity is what? 50%. Which means mass to saturate, that space is equal to what? 2 times the mass that the viscous have absorbed. So we have gotten an expression for what? The mass to saturate. So in the question they're asking, in the initial situation, when you have fresh viscous which have not absorbed any water vapor, in that situation, we know the relative humidity is 80%, right? So then what we can say is what? The relative humidity is 80%. That's equal to what? Mass available divided by mass to saturate multiplied by 100%. So mass available, I take it as X. Mass available is X. Mass to saturate is now equal to 2m, right? Mass needed to saturate is equal to 2m. That is what we found out. Need to multiply this by 100%. What you get then? What you get is, get 5 here. So you get X equals what? 8m over 5. Is that clear, everybody?
Yeah,
Are you
yeah.
all okay?
Yeah,
Okay,
yeah, that's clear. Yeah, okay.
that's clear, right? Okay. Okay, that's it. It's a short discussion, no?